There we go. All right, so good morning. Welcome back to class. The plan for today, pretty straightforward. Just continue on with chapter 3 on applications. So we're going to finish a couple of exercises and solving geometry problems, and then move on to 3.5 uniform motion applications. So that is the goal for today. Um, so yeah, oh yeah, quote of the day today. This is by Hans Zimmer. He's kind of like John Williams, if you've heard of him. He's a famous composer who writes musical scores for movies, for major films. I think Hans did Doom, Dune, D-U-N-E, not Doom. Thinking Zimmer and Dune at the same time. Anyway, um, but I saw this interview with him, and the reporter asked him something along the lines of, how would you describe your music? Um, so you might think somebody would say like, oh, classical or ethereal, or they would use some words like that. But I thought his answer was really interesting, and uh, his answer was, at my best, words will fail you because I'm using my own language. And I think this gets at the idea of the arts when they're at their best. So whether it's painting or ceramics or music or even poetry, poetry is still using words, of course, but maybe in a different way. Um, if you can summarize the piece of art using a couple sentences, well, then it's not all that interesting. The maybe most interesting art is that which is uh, so far into the frontiers of our understanding that we can't really convey the message in any other way than the medium in which it's conveyed. So we can't just say the same thing in two sentences. Um, I think that's at least sometimes when art is its most interesting. Uh, So that's the thought for today. And of course, that can quite often seem very strange as well because it's at the frontier of what we experience or able to describe or whatever. So, but yeah, I like that quote by Hans Zimmer. All right, so moving into 3.4 solving geometry applications, we talked last time about some background from geometry, and we're just going to start the day off with two exercises. So first exercise, a 10-foot string of lights will be attached to the top of an 8-foot pole for a holiday display. We're going to assume the string of lights is pulled taut so that it's a straight line. It's not like sagging or anything like that. That will be a much harder problem. Um, how many feet from the base of the pole should the end of the string of lights be anchored? And second exercise, a rectangular basketball court is 20 feet wide and 42 feet long. Merrick wants to build a fence to surround the court. He wants the fence to be a rectangle and wants it to be 5 feet from each side of the court. How many feet of fence will he need? So starting right off the bat with two exercises, let's take about maybe 7 minutes or so for these two exercises combined. And as usual, 30, 45 seconds into it, I'll kind of start writing some ideas down for the first one and then for the second one, and we'll touch base in about 7 minutes to discuss the two. Any questions on geometry, and then we will move on to 3.5. So that is the plan. So work on these two, about 7 minutes, we will come back and touch base. And of course, as always, if you have any questions, feel free to ask in the chat, or if it's easier, you can just unmute yourself and ask that way if that works better. Okay, it's a little more than 7 minutes now, so let's come back and touch base. Um, as always, if you didn't completely get through these, that's perfectly fine. Don't worry too much about it, but hopefully you were able to give both of these at least a good attempt and, ideally get a solution for at least the first one. Okay, so with these kind of word problems that are associated with something that we can draw as a picture, a lot of times it's nice to draw the picture out. So we have a 10-foot string of lights attached to the top of an 8-foot pole, and we want to know how many feet from the base of the pole the string should be. Now, there's a couple of things we have to assume here. Uh, so one thing that, and if we're looking at just the basic algebra problem, like 3x plus 1 equals 4 or something like that, right? Um, all of the assumptions are very clear. We're working with the real number system, x is a variable, like if we have 3x omitting the operator means times, all of those kinds of assumptions with notation and the kind of linguistics of things as well as the underlying mathematics, how it works, are very clear. Something like this we need to use, you might call it something like a bit of common sense. You might say, okay, like in real life, if I attach the lights like this, they're actually going to sag a little bit. It's not going to be a straight line. It's going to be pretty close to a straight line. I can get an answer that's plenty accurate enough for hanging lights by just pretending that's a straight line. Now, if I hung a 10-pound weight in the middle of it, it's probably not going to really want to be a straight line anymore, right? So it's going to put a lot more tension on it. But just a string of lights, I mean, I know I've hung Christmas lights before, it's going to be modeled as a straight line. Or maybe even more practically, you might say, well, we're in section 3-4. We haven't talked about anything with curves. We, practically speaking, have to be modeling this with a straight line to answer the question with any of the information about triangles and rectangles and things, which all have straight lines that we used in 3-4. So kind of from either the kind of quote common sense side of things or from the something like test taking skill side of things, we say, okay, this has got to be a straight line. We're also going to assume that the pole is 90 degrees to the ground, right? In reality, it's not going to, of course, be perfectly perpendicular. We try to build most things so that they're pretty much perpendicular, so the gravity is pulling the pole straight down instead of if it was tilted over, it's kind of pulling it in a way that wants to bend the pole and make it fall over more over time. So that's usually not good. So again, the common sense side of things or the practical kind of test taking side of things, if you're asked this question in section 3-4, well, if this is not a right angle, we haven't talked about how to solve those triangles. And furthermore, if this is not a right angle, we have no information about what that angle should be. So the kind of most plausible answer is a right angle for where the pole meets the ground. So I think that's another aspect that we didn't really discuss last time that can sometimes make word problems a little trickier, right? These application problems. There are implicit assumptions, and sometimes it grinds my gears how some authors write these. Sometimes I think the assumptions they make are not clear or not obvious. The problem could be interpreted multiple ways. Sometimes like here, if I was writing this up as an exam problem, I would probably, just because it's the way I think, be more explicit and actually explicitly list the assumptions on, say, an exam problem. But for like a classroom exercise or for a homework problem, I think asking you to kind of tease out those assumptions is good practice. Okay, so that was a little digression, but I think it's important to note that that's an extra challenge of word problems and application problems, that they come with a set of implicit assumptions often that are less clear, less explicitly stated than our just kind of standard algebra problems. Okay, so now with that out of the way, we have the pole perpendicular to the ground, 90-degree angle there. This little box indicating 90-degree angle. The red line is the string of lights. Now be careful that we get the numbers in the right place. So the string of lights, the hypotenuse, or opposite the 90-degree angle, is 10 feet long. The pole is 8 feet high, so the distance from the ground to the to one end of the string of lights is 8 feet. And we want to know how far away from the ground should the lights be anchored over here. And we're going to call that X. So we have assigned a variable to the thing we're looking for. That distance is going to be X. We abstract away from this diagram here, which is already pretty abstract to a diagram, but we see that we're really just looking to solve for one leg of a triangle that's a right triangle, where we have 10 as the hypotenuse, 8 as the other leg, and we want the size of this leg at the bottom here. We know that the Pythagorean theorem relates the three sides of our triangle, three sides of our right triangle. And again, we have to make sure to get things in the proper place. So we have 8 squared plus x squared equals 10 squared. 10 squared is 100, 8 squared is 64. So when we subtract 8 squared from both sides, we're subtracting 64 from both sides. We get x squared equals 100 minus 64, which is 36. And we're looking for what number squared gives us 36. That's got to be 6. So if we wanted to, do I have enough room here? Yeah. If we wanted to write out our answer, we'd say anchor the lights 6 feet from the base of the pole. A little side note here, 8 is in feet, 10 is in feet, x is clearly in feet. But we jump over to our Pythagorean theorem, 8 squared is 64 square feet, and 100 is coming from the 10 squared, or 10 squared square feet. So x squared is in square feet. And then when we square root both sides, if I ask what squared gives me 36 square feet, we're back to units of normal feet. I was writing SFT, I guess. Maybe in a math course we should write feet squared that way. But often square feet is abbreviated something like SFT or SQFT. Okay, any questions on this one? All right, in the second exercise, the algebra is a little easier, but the setup could be a little tricky. Right, I think with both of these, there was kind of the overall schematic wasn't super difficult to understand. It wasn't super abstract. It was pretty tangible. But there were little nuances that are easy to get wrong, like getting the 8 and the 10 mixed up, the height of the pole or the length of the string of lights or something like that. In this one, we have a rectangular basketball court that's 20 feet wide and 42 feet long. So I wrote that in blue. This blue rectangle is the boundary of the court with its measurements. Merrick wants to build a fence to surround the court. He wants the fence to be a rectangle and 5 feet from each side of the court. So we might be tempted to say, oh, that's going to be a rectangle that's 25 feet wide and 47 feet long. But actually, if we draw the diagram carefully, we draw the fence here. I've drawn in black. It's another rectangle that's bigger than the court. And it's 5 feet from each side of the court. That means that in the 20 unit direction, up and down in the picture, the top side of the court, we got to go 5 units higher to reach the edge of the fence, and the bottom side of the court, we got to go 5 units lower from our perspective to reach the edge of the fence. And then same thing left to right. So we actually have from our perspective, the height of the fence is 20 for the court plus 2 lots of 5, 20 plus 10, because we got to be 5 out on both of the 2 sides of the court. Right, easy little detail to miss if we don't draw the diagram. So that's one dimension of the fence is going to be 30 units. Let's call that the width. And then left to right from our perspective, we'll call that the length. The fence has got to be 42 for the length of the court. Again, plus 2 lots of 5, so that on both sides of the court, I have that 5-foot margin. Or that's going to be 52 feet. So I see that my fence is going to be a rectangle with a length of 52, width of 30. As always, length and width are interchangeable. If you called if you said that the length was 30 and the width was 52, or if when you drew your rectangle, if it was taller and skinnier, that's fine. These are all just choices you can make. Sorry, my allergies have been absolutely haywire these last few days. Okay, the next thing we have to be careful about is just not being sloppy about our formulas. So, at least in my mind, I always find it easy to make the mistake of thinking, oh yeah, perimeter is just like length plus width or something like that. But really, again, if we look carefully at the diagram, to construct this fence, I have the length twice. I have the kind of top and the bottom side from our perspective, and also the width twice, the left and the right side. So the perimeter is actually 2L plus 2W, or twice the sum of the length and the width. 2L is 104, 2 times 52, and 2W, 2 times 30 is 60. And I add 104 and 60, I get 164. So we need 164, and length is in feet, width is in feet, 2L and 2W are in feet, and I add feet together, I get feet. So we need 164 feet of fence. Any questions on that? As a little side note, what's the perimeter of the court? And it's twice 42 is 84, plus twice 20 is 40, 124. So again, if we had thought of this, again, if we weren't being careful, if we had tried to take a shortcut and said, what's the perimeter of the court? 124. Oh, and just add 10 for the height and 10 for the width, we might have got something like 124 plus 10 plus 10, or 144, neglecting the fact that we really have 1, 2, 3, 4 increases in the left to right uh, distance from our perspective, and 1, 2, 3, 4 increases by 5 feet in the up and down distance from our perspective. So again, a lot of this analysis of word problems is just taking your time, being careful. It's really these kind of silly mistakes. I call them silly mistakes when they're the type of mistake that when you look back at it, you say, oh, I can't believe I missed that, right? So not saying silly mistakes objectively, but subjectively, when you're the type of mistake where you make the mistake on an exam or something that's of high value, and you look back at it later and you immediately see what you did wrong, but it was just a little bit of carelessness that caused you to lose those points. So I think that's the other warning about applications and word problems is just take your time, draw out a picture, draw it out carefully, look at your answer. Do the units make sense, right? Does the general size make sense? 164 feet. The court has a perimeter of 124 feet. So if we were putting the fence right at the edge of the court, we need 124 feet of fence. So we know our answer's got to be bigger than 124. Yeah, so this makes sense. But just taking our time, going through everything carefully, methodically, systematically, and getting our answer. Any questions on these geometry applications? Okay, give me just 1 second here and we will jump into uniform motion applications. All right. Sorry about that. Okay, so jumping into uniform motion applications. So here formula, our main formula is going to be d equals RT, or distance traveled, equals rate of travel times time. So rate might be in, say, miles per hour, and time in hours. When we multiply miles per hour times hours, we get miles. Okay, so maybe miles per hour times hours. The hours divide out and give us miles for distance, or meters per second times seconds, you know, uh, anything kind of along that line. On occasion, we might have to be careful with units. We might be told that we're going so many miles per hour for a certain number of minutes or something, right? We might have to convert to all minutes or to all hours or something like that. But at least for these first couple, that's not really going to be a concern. But in theory, in uniform motion applications, you might have to be a little more careful with your units. But this is the formula that we're going to use in each one of these. But be a little bit careful, because it's not always often we have some variation of this formula that we're using. Maybe we're using it kind of twice in the same equation for something like that. So there are many variations on this theme. Okay, let's look at this first example. So we have a commercial jet and a private airplane fly from Denver to Phoenix. So they're both flying from one place to a second place. So they're both flying the same distance. It takes the commercial jet 1.4 hours for the flight, and it takes the private airplane 2.1 hours for that same flight. The speed of the commercial jet is 185 miles per hour faster than the speed of the private airplane. Find the speed in miles per hour of both airplanes. Okay, so again, kind of reading through it, we, I think, have the context. These two planes are making the same flight, so they're traveling the same distance. It takes them two different times to travel that distance. So clearly the commercial jet takes less time than the private airplane. So the commercial jet must be flying faster. It must be going at a faster rate. And indeed, it's flying 185 miles per hour faster than the private airplane. We want to find the speed in miles per hour of both airplanes. Let's give that, or those two variables, names. So let's go with, I would say maybe commercial and private. But the thing is, we've got a lot of variables floating around up here. Distance, rate, time. We've got a lot of different things meaning different, uh, uh, being used in different contexts. So I'm actually going to take a different approach here. Instead of saying, make my variable C and P, well, wait, is that the speed of the commercial airliner or the time it took the commercial airliner to fly? I'm going to be a little more explicit and say the rate, R, subscript C, for the commercial airliner. There's a famous physicist, his name is Richard, or was Richard Feynman, Nobel laureate, really funny and entertaining guy. If you look up his YouTube video recordings, he wasn't around whenever YouTube was a thing, but his some of his things that were recorded and filmed and either put out on broadcast or videotape or whatever have been put over to YouTube. He's a very entertaining guy, and one of the things that he said once, which kind of stuck with me, kind of in a joking way, he said, "Mathematics is the art of, of using good notation," or something like that. 90% of mathematics is notation, and there is some truth to that, like most humor, right? So coming up with a good notation that we look at it immediately and we see, okay, that's R subscript C, that's the rate of the commercial jet. So being careful with our notation, how we want to write our variables, I think is really helpful. And R sub P is the rate or the speed of the private aircraft. Okay, so we're going to use these as our speeds. That way I can say, for instance, that the time for the commercial jet T sub C, the time it took the commercial jet to fly this flight path was 1.4 hours, and T sub P was 2.1 hours. Note that our times are listed in hours, and we want rate in miles per hour. So all of my units are consistent here. My time units are consistent across the rate that I desire and the time that I'm given. So it's not like, we see the commercial jet is 185 faster, but that's in miles per hour. So everything's in the kind of proper units already. It's not like we were given our times in minutes or something and have to convert to 1.4 or 2.1 hours. All right. So on one hand, I know that let's say, distance for the commercial airliner is the rate for the commercial airliner times the time for the commercial airliner. On the other hand, I know that the distance for the private airplane is the rate for the private airplane times the time for the private airplane. But they both flew from one place to the same place. They both flew the same distance. So actually, these two distances should be equal because of that. So I see that the rate of the commercial airliner times the time that it took to complete the flight should be equal to the rate of the private aircraft times the time it took to complete the flight. So setting those two distances equal to one another, because they flew from the same place to the same place, so they flew the same distance. I know the distances are equal to one another, and by the transitivity of equality, this equals this, which is equal to that, equals that. I can equate those two right-hand sides. So this is one equation that I have. Now to keep straight what my unknowns are, maybe here I will substitute in the numbers for my times, which I'm given up here. So I have the rate for the commercial airliner. And let me move that over a little bit. The rate for the commercial airliner times the time it took for the commercial airliner to complete the journey, 1.4 hours, equals the rate for the private aircraft times the time it took, 2.1 hours. All right, so that is one equation. Here I have two unknowns, and again, remember from earlier in our applications chapter, we discussed that kind of as a general rule, if we have one unknown, we're looking for one equation, one unknown with one equation, one constraint, those kind of match up well. If I have two unknowns, I'm probably looking for two equations. I have one equation. What's my other equation? Well, we haven't used this bit of information yet. The speed of the commercial jet is 185 faster. So the rate of the commercial jet is 185 more than the rate of the private airplane. And that really just comes right out of that sentence, right? The speed of the commercial jet, that's RC, is equals 185 faster or 185 more than the speed of the private airplane, RP. So it's really just taking this sentence, converting it directly into an algebraic equation. Okay, now I would like to solve these equations, and I note that I can take this RC and swap in RP plus 185. And here my variable is just this R subscript P. If you don't like moving around the RP, if that's just, kind of strange looking to you, you can just call it X if you wanted to. Either way. But we now see that we just have a standard, plain old linear equation of one variable to solve. This does have some decimals in it, so maybe I'll multiply both sides by 10. On the left side, I only have one term. The 10 hits the 1.4 and makes it a 14. And on the right side, the 10 hits the 2.1 and makes it a 21. I've gotten rid of any decimals or fractions. I'll distribute my 14 on the left. 14 times the speed of the private aircraft plus 14 times 185 equals 21 times the speed of the private aircraft. I want to get my variable terms together. So I'll subtract 14 RP on both sides. On the left side, I have 14 times 185. I was going to calculate that out, but I think this is actually going to work out pretty nicely. This 14 will share a factor with what's left over on the right-hand side. And 21 minus 14 is 7 times the variable on the right-hand side. We've isolated the variable term. Now we divide by the coefficient to isolate the variable itself. And I'll come back over here. The rate of the private aircraft is 14 times 185 over 7, or 14 over 7 is just 2. It's 2 times 185, or 370 miles per hour for the private airplane. And then I can just come back up to one of these two equations. This is probably the easiest one to get the rate of the commercial aircraft. So the rate of the commercial aircraft is the rate of the private plus 185, or that's 370 plus 185. So I think that's 555. Yeah, 555 miles per hour for the commercial aircraft speed. So we see that we use this distance equals rate times time, but we kind of used it twice separately, equated the distances in this case. That gave us one of our equations, and then the extra information in the problem gave us another equation. We could substitute in, get a linear equation in one variable, solve it, plug back in to get the other piece of information, and there's our solution. So definitely a lot of steps, but I think each step, was fairly clear from the previous one. If I had asked you at the beginning of this problem, write out the strategy with all of the steps you're going to need to solve it, that would have been a difficult task, right? But if I say, okay, well, can you do something? Can you find a first step that you can do? A first anything you can write down? You say, okay, yeah, I know that we're talking about airplanes flying a certain distance, so I can write down my distance formula for the commercial and for the private aircraft. And then I can start thinking about those and asking what things do I know? For instance, I'm given the times. I don't know what the distance is. I don't know whether Denver to Phoenix is 100 miles or 300 miles, but I know it's the same distance that both of them traveled. If the commercial airliner went from Denver to Phoenix and the private aircraft went from Pittsburgh to Philadelphia, well, then I don't really have anything that I can work with here. right? I wouldn't be able to figure out what their speeds were. But since they went the same distance, I can equate these two distances, which means I can equate these two rate sides, rate times time. So that was really how to get my green equation over here. And then the blue equation was more straightforward to get. Okay, let's take a few minutes to work on an exercise, maybe about 4 minutes or so. So take about 4 minutes, work on this exercise. As usual, about 45 seconds in, I'll start jotting down some notes, but try to get through it kind of on your own. We'll come back in about 4 minutes and discuss the answer. Okay, it's just over 4 minutes, so let's take a look at this one. So again, Kathy and Cheryl are walking in a fundraiser. Kathy completes the course in 3.6 hours, Cheryl in 6 hours. Kathy walks 2 miles per hour faster than Cheryl. Find Kathy's speed and Cheryl's speed in miles per hour. So we know what we're looking for. We're looking for their two speeds. We'll call those R subscript K, R sub K, and R sub C. And we know the relationship between distance, rate, and time. So the distance for Kathy equals the rate for Kathy times the time for Kathy. And similarly for Cheryl. Pretty clearly here, they're walking in a fundraiser, they're completing the course. So this is presumably the same course. Again, that kind of, making reasonable assumptions. It's not Kathy completes a course in 3.6 hours and Cheryl completes a different course in 6 hours. But it says the course in both phrases, so should be the same course. So these two distances, dk and dc, should be the same. But that means that these right-hand sides have to also be the same, that the rate for Kathy times the time for Kathy has to equal rate for Cheryl times the time for Cheryl. And we're given these two times explicitly. TK is 3.6, TC is 6. So we get our first of the two equations, the green equation, 3.6 times RK equals 6 times RC. And then we're also given information about their speed differential, that Kathy walks 2 miles per hour faster than Cheryl. So RK equals RC plus 2. And what can we do here? Well, we plug RC plus 2 in for that RK in the green equation. And that yields the equation down here. 3.6 times parentheses, RC plus 2. Be careful with those parentheses. Make sure that that 3.6 is distributed to the 2 as well, equals 6 RC. We have one equation now in a single variable, and let's go ahead and solve it. So we'll multiply by 10 to get rid of the decimal, so we get 36 parentheses RC plus 2 equals 60 RC. Be careful to move that decimal point on the right-hand side as well. That 6 is just 6.0. We want to move the decimal point 1 over on the right-hand side. So don't get too lax with the details here. That 6 does need to turn into a 60 on the right-hand side. We distribute 36 RC plus 36 times 2 is 72 equals 60 RC. We have two variable terms now. We get our variable terms together by subtracting 36 RC from both sides. So I have that 72 equals 60 minus 36, or 24 RC, Cheryl's speed. And then we divide both sides by 24 to get that Cheryl's speed is 72 over 24, or 3 miles per hour. And then Kathy's speed is 2 miles an hour faster than Cheryl's. So Kathy's speed is 3 plus 2, or 5 miles per hour. Any questions on that one? Okay, let's take a look at this this problem here. This is one that the students often find challenging. They think at first glance there's not enough information to solve the problem. And we have to be a little creative when we're solving this. We have to really make use of all of the information we're given. And it's not as obvious what the end equation is going to be as maybe the previous one. Okay, so let's draw a little diagram. We see that the setup is that sisters Helen and Ann live 472 miles apart. For Thanksgiving, they meet at their other sister's home partway between their homes. So we have, let's say Helen is over here and Ann is over here, and their other sister, I don't think it says their name, but this is, say, the sister's house. Helen drove a certain time and drove a certain time, average speed. Here's how they relate. Find Helen's and Anne's average speed. And this is where people get caught up is they look at this and they say, wait, the problem is missing a piece of information. It didn't say how far the sister's house is from Helen's house and how far from Anne's. The only thing we know is the total distance between the two is 472 miles. So this is where students get hung up and they say, I don't know this distance and I don't know this distance, so I can't solve the problem. Well, let's persevere. Let's write down the information we do have. Okay, so Helen and Anne live 472 miles apart. We've got that. They meet at their sister's house that's between their homes. So we have that diagrammed here. All right. Helen drove 3.4 hours and Anne drove 3.6 hours. So we're told how much time they drove, but we're not told what the distance is between the different houses. But I do know that from Helen's house to the sister's house is 3.4 hours of driving for Helen at her speed. And I know that from Anne's house to the sister's house is 3.6 hours of driving at Anne's speed. Now Helen and Anne drive at different rates. So this would be what I'll call T subscript A, 3.6, and T subscript H, the time for Helen. Now we know that there is a distance between Anne's house and her sister's. We don't know what it is. So let's just call that dA for this distance. And let's say dH is the distance from Helen's house to the sisters. So I can actually write something down here. Maybe it doesn't feel like I'm making a lot of progress, but I can do something. I can write that the distance that Helen traveled, in other words, the distance from Helen's house to her sister's house, is equal to the speed that Helen travels times the time that Helen travels. That's just our basic distance equals rate times time. And I can write down the same for Anne. I also know that Helen's average speed was 5 miles an hour faster than Anne's. So the rate for Helen equals the rate for Anne plus 5. I've got one equation pretty easily, but what's my other equation? What's the kind of main equation doing the work here? Well, I can't equate the distance Helen drove and the distance Anne drove. The sister's house might be closer to Helen's or closer to Anne's, or might be right in the middle, but we don't know that. So I can't just equate the two. But what do I know about the distances? I don't know that they're equal. I don't know how much bigger one distance is relative to the other. But I actually know there's some. I know that the distance from Helen's house to the sisters plus the distance from the sisters to Anne's, when we add those together, that has to be the whole distance from Helen's to Anne's house. So I know the DH plus DA is 472. And this is my other equation. Or phrased in terms of things that I know a little bit more about. I know that the rate for Helen times the time that Helen drove, 3.4, plus the rate for Anne times the time that Anne drove, 3.6, equals 472. Right, so that's my more difficult equation to get. The blue equation is just, whoops, it's just this sentence. There we go. But now I have two separate equations I have two unknowns, Helen speed and Ann speed, two equations. It feels like I can solve this. I'm going to substitute in RA plus 5 in for RH, and I get 3.4 times RA plus 5 plus 3.6 RA equals 472. In this case, I'm not going to clear decimals. I think it's going to cause more of a problem than any help that it will give us. You could, it's not going to be wrong to clear decimals here, but I'll just distribute. 3.4 RA plus 3.4 times 5. Well, 3 times 5 is 15, and 0.4 times 5 is 2, so I think that is 17. Plus 3.6 RA equals, keep wanting to write the 2 too early, 472. Need a little more room here. All right, so I have now one equation in one unknown and speed. I see that I have some like terms on the left-hand side. These can combine together, giving me 7 times Ann speed plus 17 equals 472. And now we've got one equation and one variable that's in standard form. We've already got our a single variable term, so we don't need to get our variable terms together. What's the next step? Well, then we isolate our variable term. Let me subtract 17 from both sides. 7 times Ann speed is 472 minus 17. Well, 472 minus 7 would be 465, minus another 10 is 455. And Ann speed then is going to be 455 over 7 miles per hour, and I will break out the calculator for that. I'm just going to use the calculator on my phone so that I don't have to do the screen share, switch, and all that. 455 over 7 gives me 65 miles per hour. As a little side note on the units, let's kind of track the units through here. Let's just make sure all the units worked out okay. So 3.4 is a time. That's in hours. RA is a rate, a speed. That's miles per hour. 5 is miles per hour. So we're adding, right, Helen's speed is 5 miles per hour faster than Ann's speed, so that 5 is in miles per hour. Adding miles per hour to miles per hour, this sum is miles per hour. Multiplying by hours, I get miles. Similarly, miles per hour times hours, this gives me miles, and 472 is in miles. So here I have miles. Here I have miles. Here I have miles per hour times hours. The 7 carries a unit of hours. The 7 came from the 3.4 plus 3.6. They both carry units of hours. Well, coming down here, the 7 carries units of hours. RA is in miles per hour. 455 is in miles. Hours times miles per hour, the hours cancel. I get miles on both sides. That's good. And then when I divide by 7 hours, and I have 455 miles on top, there's my miles per hour. Miles divided by hours. Right. So I can always kind of track my units through and check, especially if I get an answer and enter it into the, WebAssign or something and it's marked wrong. This is a nice way to check. Or if you're on an exam and you have a little bit of extra time before finalizing that problem submission, go through and just, you can check units. That's a nice way to just check that everything worked out as expected. But here we see that Anne's average speed was 65 miles an hour. And then just to wrap things up, Helen's speed is 5 faster than Anne's, or 70 miles per hour. So again, at first glance, it almost didn't look like we had enough information because we kind of felt like we wanted to do something similar to what we did before. We wanted these two distances to be the same so that we could equate rate times time, but that wasn't the way this problem worked. So we need to be a little perseverant. We need to have a little more grit and say, okay, well, I don't know what those distances are. Let me kind of take on faith that this isn't a silly problem, right? I mean, it's if somebody just kind of gave you some random amount of information, that might not be enough information to solve the problem. But if it's in a math textbook or on WebAssign, or if we're going through it in class, somebody has probably thought through it before. Probably many people have thought through it before. And, occasionally there are mistakes in the textbook, or occasionally a mistake in WebAssign, or more occasionally I make a mistake. But that's not too often, right? Hopefully I don't make mistakes all that often. And certainly textbooks and WebAssign, when there is a mistake, people write into them and they get it corrected in the next edition for the book, or in WebAssign, just correct it kind of right away. So errors like that aren't all that common. So if you're working through a problem and you think, I don't think I have enough information to solve this problem, ask yourself, is there another approach? Is there something I can write down? Well, what I can write down, what I can do as a first step is to write down these distance equations. I know that I have the times. I know that I'm looking for the rates. How can I relate these two distances to one another? Well, I can't just set them equal to one another like I did in the previous two problems, but I note that I have this relationship between them where I know what their sum is, right? So saying, okay, I have this seemingly extraneous piece of information, 472, the distance between Helen's and Anne's house. That's not the distance that either one of them individually drove, but that's the distance that the combination between the two of them drove. And that does turn out to be enough information to solve the problem, right? So sometimes in these word problems, you kind of, your gut feeling says, I want to solve it like this, and maybe equate these two distances or something like that. That doesn't quite work out. Well, pivot, right? Uh, Say, okay, I went a little bit down this path. That wasn't fruitful. Let me back up, try a different path. Um, and a lot of times the way that you can get more ideas is just by asking yourself, what can I write down that's true, right? I know these statements are true, and this might lead me down the path to say, wait, I actually see now that I have some relationships that I can make use of. So between drawing a diagram, just like this, even for a fairly simple situation like this, drawing the diagram really helped me see the relationship between DHDA and 472, and then writing down some true things that I know to try to get me just a little bit of traction, get me moving. Any questions on this one? All right, let's take a look at an exercise then. Let's take a maybe about um, let's take about 5 minutes for this one. I don't think this one is as challenging as the last one, but maybe a little more challenging than some of the previous ones. So let's take about 5 minutes for this one. Uh, as usual, I'll start jotting down some ideas. So if you get stuck, you can take a look up, but try to do as much of it yourself as you can. So we'll touch base in about 5 minutes, discuss the answer. Okay, it was about 6.5 minutes or so. So let's come back and discuss this one. There's a couple little catches in this one. Um, so let's take a look at this. Julian rides his bike uphill for 45 minutes, then turns around and rides it back downhill. It takes 15 minutes for him to get back to where he started. His uphill speed is 3.6 miles per hour slower than his downhill speed. Find Julian's uphill and downhill speeds in miles per hour. So we have a little diagram here. This little black curve here represents uh, the hill. So traveling uphill, the green direction, he travels that at rate RU, and then traveling downhill at rate RD. The time uphill is 45 minutes, time downhill is 15 minutes. And note that we're given the information in minutes for the times, and we want our speeds in miles per hour. Now, a little aside here, I think if you just kept things in minutes, if you made that mistake, I think you'd actually be okay in this problem. Um, Not because that's fundamentally the right thing to do, but just because it's just so happens that when we get down to our equation here, we have a time on both sides of the equation. And it's just kind of a lucky happenstance that the units kind of effectively divide themselves out. So if you made the mistake of using 15 and 45 directly, um, and you say, wait, well, I got the same answer. Yeah, you probably could get away with it in this problem, but that's more a matter of luck or happenstance than a matter of kind of fundamentally good technique. We are given the information about the times in minutes, but we want the information in speed in terms of miles per hour. We really ought to convert these times to minute or from minutes to hours. That's the first little catch here. Now, nicely enough, when we write down the distance equation, the distance uphill from the bottom to the top of the hill and the distance the other way is exactly the same distance. So distance equals rate times time. So rate uphill times time uphill and rate downhill times time downhill. Those represent the same distance. They are equal to one another. But we really ought to reframe 45 minutes as 0.75 hours for the time uphill and 15 minutes as 0.25 hours, 1/4 of an hour. Or we could do 3/4 of an hour, 1/4 of an hour if you want, to use fractions instead. And we have 0.75 RU equals 0.25 RD. So this is the number of hours times the rate in miles per hour. That gives me number of miles on the left and also number of miles on the right. And our blue equation or blue sentence here gives us the blue equation. The uphill speed is 3.6 slower than the downhill speed. So rate uphill is rate downhill minus 3.6. Okay, so I can start off by, say, multiplying this green equation by 100, substituting in, and I get 75 times RD minus 3.6 equals 25 RD. I see that I'm going to have to multiply 75 by 3.6. That's going to be minorly annoying to do. So I actually might get here and choose to not clear my decimals. That's a choice I can make, right? It's not like illegal or mathematically invalid to not clear decimals or to not clear fractions, but it's usually more convenient. Sometimes it's not, though. So instead of clearing my decimals by multiplying by 100, I put a little frowny face over here because I don't really feel like doing 75 times 3.6, but I could, especially if I had a calculator. It wouldn't be that big of a deal. But if I don't clear my decimals, I notice that I have 0.75 times RD distributing down here, minus 0.75 times 3.6. Well, 3.6, 4 divides into that nicely. That's 0.9 times 4. 9 times 4 is 36, right? So 0.9 times 4 is 3.6, and I want 0.75 of that, 3/4 of that. So I want 0.9 times 3 instead of 0.9 times 4, 2.7. So 3.6 equals 4 times 0.9. So 3/4 times 3.6 is 3/4 times 4 times 0.9 or 3 times 0.9 is 2.7. So that was what I just said verbally. And that, I think that's an easier calculation to do than dealing with 75 times 3.6. Let me get my variable terms on one side. I have two variable terms. Let me get those together. And I'll choose to put them on the right-hand side just to save a step. Kind of breaking all of my rules here, but importantly, we're choosing to kind of break general recommendations that tend to make things a little easier. But if we see if we see that in a certain situation, doing something a different way could actually make the situation even better for us, we might choose that, right? So we're kind of breaking the general strategy a little bit. But importantly, we're not breaking any algebra or arithmetic rules. So I'm still just subtracting the same thing from both sides. I usually would subtract the thing that makes my coefficient positive, but then that's going to add in an extra step, and that's going to be kind of a little bit more work, a little more writing. So maybe I'll choose to do this way, right? Or maybe I'll choose to not clear my decimals. Again, that's kind of a recommended step in step 0, but maybe I see that it works a little nicer to not clear my decimals here, so I'll choose not to do that. But importantly, it's not like I'm adding 3 to the left-hand side and then adding 5 to the right-hand side, which would break an algebra rule, right? That's not a valid equation solving step. So I'm doing all the valid equation solving steps, but just making slightly different choices. 0.25 minus 0.75 is negative 0.5. And then I can divide by negative 0.5, or that's the same as multiplying by negative 2. So on the right, I just get the rate downhill by itself. And on the left side, I get negative 2.7 times negative 2. That is, I think, a positive 5.4 miles per hour. So that's the rate downhill. And the rate uphill is rate downhill minus 3.6. Five 5.4 minus 3.6. So 5.4 minus 3 is 2.4. And then minus another 0.6. That's 2.4 minus 0.4 minus 0.2, or that's 2 minus 0.2, or 1.8. So if I've done all of that ciphering correctly, the rate uphill should be 1.8 miles per hour, the rate downhill 5.4 miles per hour. That seems plausible, that seems sensible, right? That the rate uphill is going slower, it's taking more time to go uphill. So his rate uphill is slower than the rate downhill. I also see that the rate downhill is 3 times as fast as the rate uphill. 1.8 times 3 actually is 5.4, right? So the rate downhill is 3 times as fast as the rate uphill. The time it takes him to go downhill is 1/3 of the time it takes him to go uphill. That's concordant, right? My distances are the same. So if my rate gets cut by, say, a factor of 3, my time has to be increased by a factor of 3, and vice versa, to keep that distance the same. And that's what I see here. I know that the ratio between the times is a 3-to-1 ratio, and the ratio between the speeds is a 3-to-1 ratio the other way. The rate downhill is 3 times the rate uphill. The time uphill is 3 times the time downhill. So this all seems concordant with what I'd expect. I think I'm happy with this solution. Sorry about that. Give me 1 second here. Okay, so any questions on this problem? All right, let's move on to the next one then. And I think we're going to get through this problem, but probably not get to this last exercise here. So we'll do kind of what we did today. We'll start off the next class meeting with just this one exercise to work through, and then move on from there. All right, so our problem here is Lizette is training for a marathon. At 7 o'clock, she left her house and ran until 8:45. Then she walked until 11:45, covering a total distance of 20 miles. Her running speed was 6 miles per hour faster than her walking speed. Find her running and walking speeds in miles per hour. All right, so I think again, maybe if we draw a little diagram here. So she runs for a bit and then walks for a bit. Let's say that she runs at, well, I want to call the rate for walking RW, and maybe I'll just call the rate for running R subscript R. I know it's kind of strange for it to be like RR, but that way everything's kind of consistent with our notation. She covers a total distance of 20 miles. So she's running at rate RR. She left her house at 7 o'clock and ran till 8:45. Now we want the running and walking speeds in miles per hour. We would like all of our times to be in hours. So 7 to 8:45, we could think of that as like 105 minutes, but it probably benefits us to think of that as 1.75 hours. So that's the time that she was running for. And then similarly for walking, she walked from 8:45 to 11:45. The time for walking was 3 hours. Covered a total distance of 20 miles. I know that her running speed is 6 miles an hour faster than her walking speed. So rate running is rate walking plus 6. So that's my one equation that is the easier of the two. Draw that box a little better. It's the easier of the two to get. And I know that she ran a distance, let's call it D sub R, distance running. And then she walked a distance, let's call it D sub W, distance walking. Now this is kind of a very different scenario than the two sisters meeting at their sister's house in the middle. But we actually look at this picture and we see, oh, wait, this is basically that same picture. We had whoever, Helen coming from the left and meeting in the middle, and Anne coming from the right and meeting in the middle, and there were two sisters traveling at two different speeds, and here there's one person going from left to right all the way, but also at two different speeds. But we actually see that the scenario is pretty similar. So what I see is that the distance running plus the distance walking is 20 miles. The distance running is rate running times time running, or that's 1.75 R sub R. And the distance walking is rate walking times time walking, or that's 3 R sub W. That has to be 20. I jumped right into this equation a little quicker. I didn't write explicitly dr equals RR times TR, dW equals RW times TW, and equate them and or add them together and all of that. But I kind of jumped right to the rate times time side of things on the basis of these distances. Right. The more familiar you get with these, the more times you see the same pattern over and over. You can skip steps a little more easily if you feel like it. But let me come down here now and substitute in RW plus 6 for RR. And again, I think I'm just gonna distribute and solve. So 1.75 times 6 is 6 plus 3/4 of 6. Half of 6 is 3, so a quarter of 6 is 1.5. So I need 6 plus 3 lots of 1.5. That makes 10.5. 3 times 1.5 is 4.5, and add that to 6. Right, we could get rid of the decimal points by multiplying everything by 100, but then I'd have like 300 RW and 2000 on the right-hand side, and that just seems like a lot to write. I'll just deal with the decimals. I have some like terms on the left that I can combine together. 4.75 RW equals, and maybe in the same step, I will subtract 10.5 from both sides, 9.5 on the right. And then last, so I've isolated the variable term. Last, I will divide to isolate the variable itself. So RW, the rate walking, is 9.5 over 4.75, or that is 2. 4 times 2 is 8. 0.75 times 2 is 1.5. Add those together, get 9.5. And that's in miles per hour. Her walking speed is 2 miles per hour. And then her running speed, rate running, coming all the way back up here to the blue equation, RW plus 6, or 8 miles per hour for her running speed. So again, this might be one where we, at first glance, think that we don't have enough information to solve it because we weren't told how far she ran and how far she walked. But it turns out that having the total distance as well as the relationship between the two speeds and the time that she spent on each one of them, it turns out that is enough information to solve this. And that's our solution. If you want to get a head start for next time, you can take a look at this exercise ahead of time, or this exercise will be the first thing that we do when we come back. Any questions on anything from today? So I think we saw that, distance equals rate times time is a formula that we've seen for many, many years now, many times throughout school, but maybe you've seen it used in a context that, didn't seem so obvious in these problems, right? These aren't just one-step problems, person drove 60 miles an hour for 3 hours. What's the distance they went? These are more involved problems. But still, just taking our time, writing out a diagram, deciding what variables we're looking for, being careful and giving proper names to things so that we can keep track of what's what. That's why I don't like just making these like X and Y or something, because it's a little hard to keep track of what variable is associated with what thing. Even though the notation's a little more complicated looking, it's very clear when you look at it exactly what it's talking about. But kind of following all of those good steps, along with just having a little more grit, a little more conscientiousness, a little more, stick to itiveness, as they say, and saying, okay, if my first attempt or my initial gut feeling didn't pan out. Let me reverse a little bit. Let me write down something I know, or let me look for a different approach. And the more times that you see kind of similar patterns, the better you become at recognizing those patterns and making the right choice earlier in that process. Okay, so that was all that I had today. Let me stop the recording.